It's already 12:02, so I would suggest let's get started. What is on the agenda today? First, I want to give a quick introduction into the CBA process, then explain you a little bit what we can do with PowerModelsACDC. Then I'm going to go through a very quick tutorial for conducting cost-benefit analysis with PowerModelsACDC, and then just really wrap up the presentation with what else we could do actually in the future as well, again for improving cost-benefit analysis processes. Before getting started, a quick disclaimer here. So PowerModelsACDC is a research-grade open source optimization model. So the aim is not necessarily to compete with any type of commercial software tools, but actually to really provide an open modeling environment for everyone, where people can test their ideas, their implementations, and then also further develop them. So in today's talk, we really aim to just give you a glimpse of how you can set up a quick workflow and how you can get started. I have also made some code available on this, which I'm going to go through. And also a big disclaimer here, the test case that we are using are all based on open source data, so it does not necessarily reflect the real situation in terms of the cost or grid congestion or anything, but we just wanted to show that we can actually use this also for larger problems. Okay, so let's first talk about the transmission expansion planning and the role of cost-benefit analysis within transmission expansion planning. Very firstly, how does the transmission development process actually look like from an idea to the realization of the project? We very often start in the first phase, obviously, where we come up with a transmission expansion planning plan where we try to identify what are the grid needs. And in the second phase, then we are going to look at feasibility studies, basically where we try to understand which kind of investment would be the most suitable. After that, and already make actually some design decisions on the high level. This could be the voltage level, this could be the technology and so on. And then go to specification studies where we really go further and further and try to analyze actually if the new assets that we want to connect to the network will comply with all the requirements that we have. Afterwards, conduct the tendering based on the specifications that we have defined. And once the tendering is finished and the procurement is finished, the project is executed and delivered, and then eventually it is commissioned. So what I want to focus firstly is the first and the second phase, so really the transmission expansion plan, and then also some of the feasibility studies. And when we are talking about transmission expansion planning, we need to actually answer 4 fundamental questions. The very first one is actually, where do we want to invest? So which particular connections should be built or extended? The second one is going to be the type of investment. So which technology do I choose? Are these going to be AC connections, DC connections, overhead lines, underground cables? Are these going to be battery investments, STATCOMs, whatever technology that you actually think of having in your grid? Another important question is also to understand when to invest. What is the best possible time point or the sequence of grid extensions? I will also come to that actually at the later or at the end of the presentation as well. And the fourth one is basically who pays for it, or how do I get remunerated? So how are my investment costs and future revenues allocated? Because that is also going to have an impact on my investment decisions inherently. So what is the role of a cost-benefit analysis in the development process? This falls under the phase 1, transmission expansion planning, where basically one tries to first identify the grid needs. So where do I have congestion, or where do I actually observe, let's say, large price divergences in my grid? And after that, I'm going to define a number of candidates and then carry out some planning studies. And this is going to involve some technical evaluation, some economic evaluation, and some social and environmental evaluation. So I took this figure actually from an IEEE report that we wrote back in 2021, which is called Studies for Planning HVDC. So basically why you're here, that's the reason why you see here as a decision or an outcome. If we had basically the investment decision for a DC link. However, of course, this could be applied to any other type of investment as well. So how do we actually do network development studies? The very first starting point is obviously to start from a number of scenarios that will encompass different possible futures. So the way we approach this in the ENTSO-E is, or in Europe is, within the ENTSO-E's 10-year network development by using different macro scenarios, and the let's say the three main scenario sets that are being used are what is called a national trend scenario, which is somewhat of a continuation of business as usual. Then a distributed energy scenario where we have many distributed assets across the grid, and then a global ambition scenario, which again goes towards 100% renewable future, or basically a carbon-free future, but then concentrates on larger assets. And then within each scenario set, one will also then analyze different climate years and different planning years in order to eventually cover the whole range of uncertainty towards the future. In a second step, what we do is to actually conduct some market studies to identify the economic balances. Again, this is a figure that I took from the ENTSO-E TYNDP procedure, so from the 10-year network development, basically where then a European market simulation is run, considering the cross-border congestion that one might have, and based actually on the outcome of the market studies, we can observe at which border, which kind of price differences that we have, because this now gives us a high-level indication of where actually to put interconnectors and where to increase the transmission capacity. Of course, with such a model, we can only focus on the cross-border assets and increase the cross-border transmission capacity. This does not necessarily tell us which exact lines we want to build, especially if we have a lot of internal congestion, which has a large impact. Then we also need to go, of course, to a more detailed model. This is also what I'm going to talk about today. And in the very last stage, one can then also try to understand basically what the grid transfer capacity is that we have, and also what the bottlenecks are, which eventually cause these different price divergences. And one could also try to understand how much additional capacity should be built in order to actually resolve this. In terms of the technical evaluation, what we usually resort to is steady state analysis. These are going to be some power flow calculations, maybe some short circuit calculations if we already need to think about extensions of some substations. For instance, can our circuit breakers already handle these things? One can try to look at analyzing different high-level control actions and protection requirements, and then also analyze different topological actions. Towards the more specification studies, actually, so maybe not necessarily in the very first investment option analysis, one can also resort to transient analysis, but this is usually already a step further than what we would do in a techno-economic study. Okay, so how can we actually approach techno-economic system studies using PowerModelsACDC? How does market modeling happen in general? This is typically done using unit commitment type of models. So in Europe, most of the transmission system operators will use either Plexos or Antares. Here we usually have a more simplified representation of the power grid due to tractability issues. So this will be most of the time a net transfer capacity based model, or sometimes it is going to also involve some impedances or power transfer distribution factors, PTDFs, that will then eventually represent the distribution of the power flows between the different zones. But more often than not, we are not going to use a very detailed model of the transmission system. In these kind of unit commitment problems, we also typically have some integer constraints that are going to represent the thermal characteristics of generation. It is going to be a 1 node per market zone model. And what we then usually do here is to really assess the adequacy of the system also by modeling the expected energy not served. So either the demand is modeled as something flexible, or we introduce a fictitious generator, which is going to represent the expected energy not served at a very, very high cost, and is going to make sure that the model always finds a feasible solution. And in a post-processing step, one can then also do is to actually calculate the indicators and to understand how much more renewables we are integrating in the system, and to what extent we are also reducing emissions. These type of models can be deterministic or stochastic. So most of the commercial tools are going to give you a deterministic solution. But of course, if you perform these things, I would say in a more Monte Carlo approach, or modeling different climate years and different planning years, you will be able to cover a large scenario set. When we are doing congestion analysis, so really understanding where in the system we have bottlenecks, we are going to utilize most of the time power flow or optimal power flow models. So this can typically be done using nonlinear AC power flow models. This also allows us actually to quantify the system losses and potential voltage management issues. However, when we are using AC power flow calculations, especially on large systems, it can really lead to large convergence issues in ill-conditioned cases. So very often, if you need to solve power flow models thousands of times or potentially millions of times, you still will resort to linearized models, which eventually just going to have a better convergence behavior. But to deal with this, we already do have a number of commercial and open source implementations. And basically, when we also want to model the controllability through phase shifters, HVDC links, then often an optimal power flow model could be needed, because this is going to tell us how we should optimally set the set points of all these devices. Because if you want to brute force them across the whole range of controllability, then you really end up having to cover a very large search space. And if you're relying on mathematical optimization, you can actually do this in a more efficient way. However, what we of course always need to understand is that from the higher level market models, that we actually need to come towards a more detailed grid model. And for that purpose, we usually end up doing a lot of model disaggregation, which is then going to project the market outcome on the more detailed grid. And this is very often subject to assumptions, and this is also one of the, I would say, more difficult and opaque points between different types of planning models. Okay, so this is going to be our basic workflow for today as well. We are going to start from a market modeling approach, and then we are going to use a more detailed grid model in order to understand what type of benefits some HVDC links are going to bring us in a system in the practical example later. Maybe also here a quick introduction of where now PowerModelsACDC fits in this workflow. PowerModelsACDC was first developed with the idea of solving optimal power flow type of models for AC and DC grids. So what type of functionalities does it already include? It has it has two different power flow formulations. One of them is a genuine Newton-Raphson based formulation, and another one is where the power flow is actually implemented as a feasibility problem and is solved using an interior point method. The latter one usually does converge a little bit better, but then also suffers from higher computation times. Then, of course, there is an optimal power flow model, which is going to optimally determine generator set points, but then also set points of your storage devices, HVDC links, phase shifting transformers, and so on. It also includes a transmission expansion planning model, which is going to determine which exact AC or DC links you would actually build in your system. I would say a slight deviation or a slight evolution of the optimal power flow model is also a redispatch optimization. So here you basically use the same grid constraints, but your objective changes. And instead of minimizing the dispatch cost, here you're trying to minimize the redispatch cost with respect to some reference values. It also comes with a unit commitment model and also a range of change of frequency constraint unit commitment model. So here you are also determining which generator should be on or off at what given point in time. And basically, if you then also consider the inertia that you need in the system to limit your rate of change of frequency, you can also do that with this Rocoff constraint model. The package also includes a basic security constraint optimal power flow model, which is going to make sure that whatever dispatch schedule that you come up with is going to comply with N-1 constraints. And we hope to also include a optimal transmission switching model soon, which is at the moment being developed in a separate package, but in the course of a PhD thesis. And we are going to also merge this hopefully soon into PowerModelsACDC. It also comes with a list of different power flow formulations, because when we are looking at long-term planning problems, in order to increase the tractability of the models, very often we want to linearize our power flow equations to be able to use more performance solvers. However, of course, when we need to look at how to do voltage management, how our losses are going to be affected, and so on, then we also need the full set of nonlinear equations. And between the linear formulations and the nonlinear equations, we also have a number of different relaxations, so quadratic or second-order cone formulations as well. And the whole tool is built up in a plug-and-play way that you can just choose which formulation that you want in order to solve the type of problem that you want to solve. And this package also serves as a backbone for further tools that have been extended on its basis. So we also have a specific implementation which allows us to model unbalanced DC grids, where we would have a full bipole representation with a dedicated metallic return. And for instance, we could also then simulate what is going to happen if we have a pole outage and how the power flows and the voltages are going to be. It is also used as part of an ACDC grid state estimation tool, a tool called FlexPlan that was developed in a European project, which looks at combined expansion of transmission and distribution grids, and then also a quiet performant security constraint optimal power flow model, which was built based on the ARPA-E grid challenges reference implementation. So this was really developed to solve such a problem within a few minutes. And this has then also been tested on the Australian power system in order to do a quasi real-time security constraint dispatch of the whole grid. So what is the optimal power flow problem in its general? The objective is we try to find the cheapest combination of active and reactive power generation. And this optimization problem is subject to the circuit physics that I need to respect, basically Ohm's and Kirchhoff's laws. I have to respect the operational limits of my system, the currents and the voltages, and then also the technical equipment limits. These can be, again, currents, voltages, or some stability limits, for instance, as in the case of the Rokov constraint unit commitment model. And basically, the optimal power flow problem is more a generic name. You can change your objective and then try to optimize voltage profiles, minimize network losses, and so on. But of course, whatever you do, you will always have to somewhat penalize your generation cost, because otherwise you're going to get unrealistic solutions. So how do we approach this within PowerModels ACDC? If you're not a mathematician or a computer scientist, but I would say a power systems engineer, this is sort of the workflow that you use to approach an optimization problem. So you first basically define the set of equations that you're going to solve, and this is going to give you a mathematical complexity class. After that, you're going to use a modeling language, which can be in Python, in Julia, or it can be in commercial software like Ample or GAMS. Then after you have formulated your model, you're going to actually take a mathematical solver. Again, either something commercial like Cplex or Gurobi, but then you can also find open source solvers like HISE or IPOpt, at least for the research community. And these optimization solvers then in the background are going to use some sort of algorithm to solve the problem. And PowerModels ACDC basically uses the Julia language as a modeling language and then formulates all these different types of problems that I was talking about in the Julia jump framework. So very briefly, how does the optimal power flow model look like? So we will try to minimize the active power generation cost, which typically is formulated using a quadratic equation, where here PG is the generated power. And then we are going to fulfill Kirchhoff's current law, both for active and reactive power, or formulated around active and reactive power. So basically, the sum of all the injections need to be the sum of all the outtakes. Then Ohm's law for the AC lines that we have, but these can also represent transformers and so on. So we are going to formulate this obviously in real numbers, as optimization solvers cannot cope with complex numbers. And within PowerModels ACDC, we have the typical pi formulation with the series conductance and admittance, as well as then shunt susceptances and capacitances. Then we are going to give our AC equipment also the proper limits. So active and reactive power generation limits, apparent power limits, on the branch flows, angle limits, then our operational voltage limits as well. When it comes to modeling DC branches within PowerModels ACDC, we have basically two formulations. It is a balanced formulation in any case, so voltage imbalance is not necessarily modeled, but we can still choose between a monopolar or a bipolar HVDC, which is going to have an effect, of course, on the losses. And again, these can be modeled either explicitly by explicitly modeling the current that goes through DC links, but then also where the current variable is expressed as a difference of voltages, what we then also call a bus injection model. Then for the converter station model, we use a parametrized model, basically where we have the model of a transformer, then a filter that is going to consist of an inductive and a capacitive part, and then eventually the power electronic converter in itself. But for instance, if you have an MMC type of converter, you might not necessarily have a large filter, so you can actually omit this filter part out of your equations just by setting your filter parameter to 1 or 0. And the same thing you can actually do also for your transformers as well. And this way, it actually allows you to model MMCs, 2 or 3 level VSCs, but LCCs as well. So the power electronic converter in itself is modeled between the AC and the DC side via the coupling of the energy. So we are defining that the AC side power and the DC side power needs to equal, or the sum of them needs to equal to the losses. So we are choosing here a convention where basically both powers are going in. And basically the loss function is then expressed as a function of the converter current in itself, and also linked to the AC side voltage of the converter. And of course, when we have LCC type of converters, then we also need to additionally have a link between the AC and between the active and the reactive power, as these are going to be defined by the firing angle that we have. The AC part of the converter station is going to obey exactly the same equations that we had before for modeling AC lines and transformers. So at the end of the day, nothing really new there. So here is just the set of formulas, but also if the slides are shared later, these are put here just as additional information. And last but not least, at the end, we are going to put the AC and the DC grid together, again, using the Kirchhoff's current law, both for the DC nodes that we have in the grid, but then also for AC nodes, where we would have classically, besides generators and loads, then also the converters that are injecting power into the system. So let's try to have a quick example of conducting a cost-benefit analysis using PowerModelsACDC. Here, a quick reminder actually of the SOC-CBA guidelines and the process. So within the SOC-CBA, we try to monetize social welfare benefits, CO2 emissions, variation of grid losses, reduction of redispatch reserves, and also adequacy needs. And this is typically done, again, using a market model where then the socio-economic welfare is determined. The CO2 emissions can be then actually also directly monetized via the emission cost in the objective, because the emissions will be directly linked to the output of thermal generation or fossil fuel thermal generation. Most of the time, the market clearing will be a linear model, so the variation of grid losses is usually then done using power flow calculations with the obtained dispatch, and is usually not really optimized. For the reduction of redispatch reserves, again, usually this will be done using a contingency analysis with the obtained dispatch, and this could also be optimized. And the adequacy will be some post-processing based on obtained dispatch, and again, a flexible modeling of node or a fictitious energy not served generator. So the process that we are going to follow today is actually where we will start from renewables and demand time series. Then we are going to solve an NTC-based zonal 10-year network development plan model, where we are going to obtain the generation dispatch per generator type. The reason of doing that is that the TYNDP input data set that is published by ENSOE only provides this per type and not per generator. And after solving this NTC-based zonal model, we are also going to obtain some interzonal exchanges, basically how many megawatt hours are exchanged at each hour of the year between the different market zones. With that, then we are going to go to a nodal disaggregation and to a more detailed grid model, and where we are going to use some nodal renewable generation and demand profiles. And to actually conduct the cost-benefit analysis, we are going to run an optimal power flow model without the investment, and at the same and in a parallel calculation, the optimal power flow with the investment. And after that, we will be able to compare the results. And for the case study that we are going to look at, we are going to take the example of the 3 HVDC corridors in Germany, basically the Ultranet project, which is a multi-terminal DC link. So basically having 3 terminals, and then 2 point-to-point links, which is the Südlink and the Südost link. And if you actually look at the actual assessment of the that has been conducted, you can actually see what the social welfare benefits for 2040 are as projected, and these are then the social welfare benefits that are brought per year. I also calculated them and put them per week because the calculation can take quite a long time. For the script that I prepared for you, I have only done this calculation now for a week, which is going to solve with an open source solver roughly in about 3 minutes. And as the grid input data, because the ENSO-E data set only involves the zonal market clearing model, we are also relying on an open source grid model, which is the representation of the European 400 and 220 kV grid. And basically here, the German grid model will have about 1,000 AC nodes, about 1,300 AC branches, some 1,500 generators, and 43 HVDC links in total. And before going to the hands-on tutorial, we will use a Pluto notebook that you can also find under the given link here. So I have uploaded it this morning to the repository of PowerModelsACDC. PowerModelsACDC in itself is written in Julia. So for being able to use that tool, you will have to install Julia, for which you can also find the download instructions here. If you need a coding environment, usually Visual Studio Code works best for it, which is again an open source development environment. And once you have installed Julia, you can actually just import the Pluto package and then actually run the notebook as it's on the repository. Okay, so let's try to switch to our quick tutorial. This is obviously the wrong page. Yes, here we go. So in this tutorial, basically, or in this Pluto notebook, you really have the step-by-step instructions of actually setting up a very nice workflow. So here a quick description. We are going to perform a typical cost-benefit analysis, and for that we are going to use the data from the TIVA NDP 2020. The calculations are based on the climate year 2007, and then for the distributed energy scenario, as we are relying here on an open source grid model, the ratings of the power lines are not always very consistent. So I have here just made, I would say, a deliberate choice of limiting them to 1500 MVA for all the internal lines that we have in the German grid. And the HVDC links are going to be evaluated one by one, and then eventually also all together. So first, the notebook is going to run the zonal market clearing, and then the results will be used on the more detailed German grid model to actually assess what the HVDC links are going to bring us. In order to prepare the data, we are also relying on a package that is called EU Grid Operations. This is also available in open source. I have also provided the link for that. at the end of the day, what you need to do is going to be to download that package and somewhere on your local hard drive. So you can see I have done it for my local hard drive as well. And then this piece of code is going to make sure that you can actually get all the data that is in there to be able to run the package. So this is actually the first blocks that you're going to see are here really just to define the input parameters and do some quick manipulation of the input data. So I'm not going to go line by line through the code, but just to give you a little bit of a glimpse of how you can actually set this up for yourself. So what we are doing here is really to define how many hours we are going to run the simulation for, from which hour in the year we are going to start. So I have just randomly picked I would say, I guess, a day in late spring. And then we define our distributed energy scenario, the planning year that we are looking at, and then the climate year. And these are basically just some additional settings that we can then set to use some function in the code. So in the very first part of the code, what we are going to do is we are going to get all the input data that is coming from the EU-Go package. And these are actually taken care of by these functions. Then we are going to run our zonal market clearing model. So for the zonal market clearing model, we have a network flow model, which basically, or an NTC-based off model, which means we are not modeling any type of ohms or Ohm's law. And actually only make sure that the nodal power balance is kept and the power flow between the different zones is going to be smaller. Is going to be smaller than the large. Smaller than the net transfer capacities. Here again, just some auxiliary functions. It can happen that due to the input data, sometimes your optimal power flow solution is going to be infeasible when you're going to the more detailed grid model. So as such, we have here some auxiliary functions which are going to track if this happens or not in order to avoid for the calculation to terminate due to an error. And what is basically going to happen is it is going to initialize the result with 0 if this happens, and then also discard these hours from the post-processing. And as already mentioned here, as the power flow limits are not very consistent, we are doing here a manipulation of them. And there are also some other inconsistencies in the grid model that I found recently, which are, for instance, that there is a strange fictitious AC connection between Belgium and Germany and so on. And these are then have to be manually deleted out of the grid model. So when you then actually run the zonal model, this is the typical output that you can get, where you can actually see the objective function value, and then how the optimization has terminated. And again, this calculation is now going to give us the generation dispatch per type. So how many megawatts of renewables are being dispatched, onshore wind, offshore wind, solar PV, how many megawatts of gas is dispatched, how many megawatts of coal is dispatched, nuclear is dispatched, and so on. And it also then gives us the power exchange between the different market zones, for instance, between Belgium and Germany at that given hour. And when we are then solving our more detailed optimal power flow model to understand the effect of these 3 embedded links, what we actually also need to do is to fix the exchange, because now we are changing our grid model. And if we would not fix this particular exchange, then we would get solutions that are not consistent with the market outcome. So for that purpose, also in PowerModelsACDC, a function is or a constraint is implemented where you can really use this functionality if you have defined borders at your grid data, that the interconnecting flows on the borders are going to be fixed. Here is also just some snippets of code that you can use yourself to actually save your results, but I have not activated it by default. And in the same way, there are also some functionalities where you can actually plot the results of your power flow calculations and optimal power flow calculations, which will then produce you pictures like this. So as the time is progressing, I'm going to quickly go towards the results of it. So at the end of the day, we are solving the model optimization problem. Then for the hours that we have defined, for the base case where we don't have any investment, and where we then only add the pseudos link, the Zoot link, or the Alternet connection, and then eventually all candidate links as well. And here you can see then the size of the system. And this part of the code is basically just going to take care of initializing your results. And then at the end, the actual optimization happens here, basically for each of the hours that we have specified, and then also for each of the links that we have here. And at the end of the day, the optimization results are going to be written out. So what you can see here is the hourly dispatch cost that you would then expect in Germany for that particular hour in 2040. And again, this is then given for all the options that we are looking at, basically for all the candidates, but then also for the base case at the end of the day. And if you then eventually aggregate all these results, we can see here the social welfare increase in million euros. So for the 1 week of operation, we would get for the Zoot link a cost reduction of about 10 million euros, for Alternet about 2 million, and for Zoot link for about 9 million euros. But as said, as the calculations are subject to an open source grid model, where then also a lot of assumptions go into generation costs, etc. Take these results only as something very, very indicative, obviously, but this is just here to show you the principle of what you can actually do with it. And at the end of the day, you can obviously also visualize. So here you actually see your, maybe one thing to mention here, in a post-processing stage, you can also see how much more renewables you're generating if the HVDC links are in place, to what extent you're actually decreasing renewable curtailment, to what extent you are decreasing emissions, and what then also the effect is on the adequacy of the system. And a different representation of the results are also given here, where you can actually see the total operating cost, but maybe more importantly, how you can actually, or how much money you're saving in each of the operational hours. And you can see that there are some hours which where the operational cost savings are much, much higher. And these are usually hours that you would typically associate with adequacy issues, or where you would have to do load curtailment for whatever reason. Again, just a different representation of the benefits than here as a bar chart as well. And with that, we can actually conclude, I think, the webinar. So maybe just give you a quick outlook as well. So at the end of the day, when we are talking about DC grid investments, I think we also need to move towards least regret and multi-value planning. Why least regret? Because there's a large scenario uncertainty with respect to the future of the energy systems. This can be prices, this can be the role of molecules, this can be policy changes. As such, what one needs to do is to really obtain least regret decisions for the immediate future. Maybe if you're looking 5 to 10 years ahead, that you actually invest into lines or grid expansion that is going to give you definite benefits and everything that is more uncertain, you will choose to do in the future. But to be properly assessed that, we need to move more towards stochastic models for risk-based decision under uncertainty, which is what we are also working towards to. And why multi-value? If you have been following the news, there has been quite a lot of increase in the cost of power system equipment, both for AC equipment, but also for DC equipment. On top of that, also the characteristics of the power system are fundamentally changing with the power electronics. So when we are then actually looking at capturing benefits of a certain investment, we also need to take into account how does this contribute to stability or maybe even to resilience, to really have a more comprehensive cost-benefit analysis, which then also means that we need to embed different types of frequency, voltage, or potentially harmonic constraints in our optimization models. And this is basically also still ongoing research here at Edge. And with that, I want to close the webinar here and take the remaining 13 minutes to actually have a discussion and go through the questions that you might have posted.
Okay, thank you, Hakan. We have some questions. The first questions were about the practicality, so whether we will share the slides and the webinar. So we will definitely share a recording of the webinar on our website, and the link will also be shared via email to all the participants. Another question was already largely answered, but is this an open source tool with access to the public?
Yes, this is an open source tool with access to the public. It also supports the usage of basically any type of optimization software that you want to use. So the modeling in itself is open source. You can also run your optimization using open source solvers like HISE or IPOpt, but you can also use commercial solvers like Gurobi or Cplex. So it is sort of a plug and play solution. Obviously, if you're using these commercial solvers, then you will just get more performance out of it at the end.
Okay, thank you. Another question. The CBA shown in the example does not seem to include intertemporal constraints. Can these be modeled in PowerModelsACDC?
Yes, and in fact, they are modeled. So here I wanted to keep the example that I have, I would say a bit lean, but PowerModelsACDC supports also storage equipment, for instance, and also the unit commitment model includes actually all these time coupling constraints. Having said that, this is not a commercial implementation, right? Like Plexos or Antares, where these things are usually implemented in a bit more performant way. But generally, you can also run problems or you can calculate problems like that as well. But then you will need to be aware that the problem size that you're going to give cannot be too big. So if you want to run these things for an entire year for a system, you know, like the size of Germany, then this might not necessarily solve. So for that purpose, you might first have to also resort to clustering approaches, etc., in order to reduce a bit the dimensionality of your problem.
Okay, thank you. Another question. Very interesting tool. Do you have kind of manual and software requirements? Do you plan to organize training for users and any examples on more simple examples?
So absolutely. So I think there is the tool already has a documentation which outlines basically how you have to run it, which problem types are implemented, and the mathematical models of the different devices. Generally, if there is, I would say, requests, we definitely would like to have also more hands-on training with respect to the software requirements. As said, if the only thing that you need is to actually download Julia, which is an open source general purpose language such as Python. And if you're actually using open source solvers to run it, Most of them are also genuinely implemented within Julia, so you don't even have to install anything different or anything other than Julia. But if you need to restore it to commercial solvers, obviously you will have to have the licenses for these commercial solvers, and you will also have to install them. And yeah, I think I might have chosen here a bit of a more complicated example as well. But generally in the repository in itself where the software is located, we also have just some simple examples where you can run investment type of problems or optimal power flow problems just on, smaller IEEE systems and so on as well, to play around with it and to extend it yourself.
Okay, I have also posted the link to the tool in the Q&A itself. Another question, could the flow-based clearing be implemented in PowerModelsACDC?
Generally, yes, because the flow-based market clearing essentially is not so much different than having a DC power flow model. So there we then have basically some impedance information that we can then also embed within PowerModelsACDC. So once you actually know what the equivalent impedance is or the power transfer distribution factors are, you can actually also easily embed them into PowerModelsACDC.
Okay. What other devices are modeled in PowerModelsACDC? Is it specific to HVDC links and AC lines and cables?
No, I said so. Storage devices are implemented, so there is a basic implementation of a storage device. Again, formulated either as a lossless linear model, but then also a lossy nonlinear model that you would connect via inverter to your AC grid. And obviously the storage model then also, models the state of charge and all the proper limits for your energy capacity and your charging and discharging. There is also a model of phase shifting transformers and also a model for static series compensators, which is basically also a power flow controlling device. We are also extending the tool within the Prosecco project, which is a Horizon Europe project now, also with a DC power flow controlling device. When it comes to the optimal switching, then obviously power switches are modeled. So basically we are trying to extend the tool based on the functionalities that are being requested either within some projects that we have, but then also people who are using the tool and would like to see these devices modeled.
Okay. In the future, will you have standard costing and technology for HVDC?
I am not sure if I fully understand the question of what is being meant with standard costing. But in the transmission expansion planning type of model, basically also the cost of the DC links you have to model. So this is something that you would typically give as an input. So in the actual implementation of the expansion optimization, we have a binary decision variable, which is going to tell you if a certain converter station should be built or not, and if a certain DC link should be built or not. And you can then provide this, the cost of these things as an input to your optimization model. And then at the end of the day, the optimizer will then choose the best combination of converter station and DC links to be built. Obviously, we do have some idea of what realistic costs are, but usually, yeah, when we are so in the package itself, you will find a lot of academic test cases, obviously. But then for these academic test cases, it does not make sense to provide also realistic cost for the DC links, as these cost figures are usually, or the operating cost of the system is usually also not very realistic. So long story short, you can provide basically the cost information as your input for your investment optimization, but then you need to choose these things also wisely and obviously reflect, what is at the moment realistic costs.
Okay, thank you. I don't think there are any further questions.
Okay, then I suppose I thank everyone for joining and taking the time of being here, and hope to see you soon in the next webinar. I would also suggest, if you have particular ideas of study cases that you would like to see, or any other type of hands-on examples of how to use it, please reach out to us, and then we can try to put something together and in a new edition of such a webinar in a short time, hopefully. So see you soon again, and have a great rest of the afternoon. Bye-bye.